6 months ago, a team at a major fintech company pushed a routine deployment. Within 4 minutes, their AI observability platform detected an unusual memory pattern in their payment processing service. Not a crash, not an error, just a pattern that had never occurred before. The system automatically correlated that signal with a similar event from 3 years prior that had eventually caused a full production outage. It flagged the deployment, triggered a rollback, and sent a notification to the on-call engineer. The engineer was asleep. The system fixed itself. That is not a futuristic scenario. That is happening right now in 2026. And if you are a performance engineer who is still doing this the old way, manually analyzing dashboards, writing static thresholds, running the same load test scripts you wrote 2 years ago, then this video is your wake-up call. My name is your host here at Performance Engineering Academy, and in the next 30 minutes, I am going to walk you through every major shift happening in AI systems performance engineering right now in 2026. We will cover AI-driven observability, self-healing Kubernetes clusters, automated root cause analysis, AI-augmented load testing, and I will tell you exactly what the new performance engineer looks like in this world. Let us get into it. Before we go deep, let me give you the honest picture of where we are coming from. For the past decade, performance engineering has been fundamentally reactive. Something breaks, you look at the graphs, you find the bottleneck, you fix it, you write a postmortem, and you try to prevent it from happening again. The entire discipline was built around human observation speed. And that worked, until systems became too complex and too fast for humans to keep up with. In 2026, a modern microservices architecture running on Kubernetes in multi-cloud environments can generate hundreds of millions of telemetry signals per hour. Traces, metrics, logs, events. No human team can process that volume in real time. No static threshold system can adapt to the natural variance of those systems. And no manual load test written 3 months ago can predict how your system behaves under an AI-generated traffic pattern it has never seen before. This is the fundamental problem AI is solving right now. Not replacing performance engineers. Extending what performance engineers can see, predict, and do. So let us start with observability, because this is where the most dramatic changes are happening. Section 1. AI-driven observability. Traditional observability has 3 pillars: metrics, logs, and traces. You have probably heard that before. But here is what nobody talks about. The traditional observability stack was designed for humans to consume. You set a threshold, you get an alert when the threshold is breached, you go investigate. That model is fundamentally broken at modern scale. Think about what a static threshold actually means. You are saying that if CPU usage goes above 80%, something is wrong. But is that true at 2 a.m. on a Tuesday when traffic is low? Is that true during a flash sale when 80% CPU is completely normal and expected? The answer is no. Static thresholds generate noise, and noise trains your engineers to ignore alerts. That is called alert fatigue. And alert fatigue kills systems, because the one real alert gets buried in 200 false ones. AI-driven observability solves this with dynamic baselines. Instead of asking you to define what normal looks like, the system learns what normal looks like. It builds a statistical model of your system behavior across time of day of week, deployment frequency, traffic patterns, and dozens of other signals. It knows that your checkout service always spikes on Saturday mornings. It knows that your recommendation engine uses 20% more memory after each model retrain. It knows your baseline. And when something deviates from that learned baseline, even before a threshold is breached, the system flags it. This is called anomaly detection. And in 2026, the best platforms are doing this at the infrastructure level, the application level, and the business metric level simultaneously. That means the system can correlate a subtle increase in database query latency with a drop in conversion rate and a spike in cart abandonment, all before your P99 latency metric crosses any threshold at all. Tools like Dynatrace Davis AI, Datadog Watchdog, New Relic NRAI, and open source platforms built on OpenTelemetry with AI inference layers are all doing this today. But here is the important engineering detail that most content skips over. The quality of your AI observability is entirely dependent on the quality of your instrumentation. If your application is not emitting structured telemetry, if your traces are incomplete, if your logs are unstructured strings instead of JSON with consistent field names, then no AI system in the world can help you. Garbage in, garbage out. This is why instrumentation standards like OpenTelemetry are not optional in 2026. They are the foundation that makes everything else possible. Another important concept here is topology-aware observability. Modern AI systems do not monitor individual services in isolation. They build and maintain a real-time service dependency map. They know that service A calls service B, which depends on database C and message queue D. When something goes wrong, the AI traverses that dependency graph and identifies the root cause node, not just the symptom node where the error first surfaced. That capability leads us directly into our next section, which is where the real magic happens in 2026. Section 2, Self-Healing Kubernetes Clusters. If AI observability is about seeing problems earlier, self-healing is about fixing them without waking anyone up at 3 a.m. Kubernetes already has some built-in self-healing. If a pod crashes, it restarts. If a node fails, pods get rescheduled. You have been working with this for years. But what I am talking about in 2026 is a completely different level of intelligence. Traditional Kubernetes healing is reactive and mechanical. Pod crashed? Restart it. That is a rule. AI-driven self-healing is predictive and contextual. Memory usage has been climbing at a specific rate for the past 40 minutes, and based on historical patterns, this pod will OOM kill in 14 minutes, trigger a controlled restart during the lowest traffic window in the next 8 minutes, and simultaneously scale out one additional replica to absorb traffic during the restart. That is an inference, not a rule. And that distinction is everything. The platforms making this real in 2026 include Carpenter with machine learning extensions for intelligent node provisioning, KEDA with AI-powered scaling triggers that go beyond simple queue depth metrics, and platforms like Commodore and Cast AI that use ML models trained on historical cluster behavior to make preemptive remediation decisions. Let me give you a concrete architecture pattern that leading SREs are deploying right now. It is called a closed-loop remediation system. Here is how it works. The observability layer detects an anomaly and generates a signal. That signal goes to an AI inference layer that classifies the anomaly type: memory leak, traffic spike, configuration drift. Based on that classification, the system selects a remediation playbook, not a static runbook written by a human. A dynamically generated action plan that the AI has learned produces the best outcome for this specific pattern of symptoms. The action is then executed by an automated operator, either a Kubernetes operator or an Ansible automation with a confidence threshold gate. If the AI confidence in its recommended action is above 90%, it executes automatically. If it is between 70 and 90%, it executes and sends a notification. Below 70%, it pages the on-call engineer with a pre-populated diagnostic context, so they can start informed instead of starting blind. That confidence threshold gate is the most important design decision in the entire system. It is how you prevent the AI from making a bad situation worse. And it is what separates mature AI-driven operations from chaotic automation that your team will stop trusting after the first bad experience. Now, here is the critical thing I want you to understand about self-healing. Self-healing is not a replacement for good engineering. A system that keeps healing a bad design is not a well-engineered system. It is a system that hides technical debt. The goal of self-healing is to handle known failure modes automatically, so your engineers can focus on systemic improvements, not on fighting fires they have fought 50 times before. Section 3. Automated root cause analysis. This is the section I personally find most technically fascinating in 2026, and it is also the area where I see the most confusion about what I can and cannot actually do. Root cause analysis has traditionally been the most time-consuming and most expertise-dependent part of incident response. A senior engineer looks at a dashboard, mentally correlates signals across 3 different monitoring tools, remembers a similar incident from 8 months ago and figures out that the real problem is a slow database query introduced in last Tuesday's deployment. That process can take hours, and it depends entirely on the experience of the person doing the analysis. Automated RCA in 2026 is attempting to encode that expert reasoning into a system, and the results are genuinely impressive when the underlying data quality is there. Here is the technical architecture of how the leading platforms approach this. The first layer is causal graph construction. The system builds a directed graph of your entire architecture, where each node is a service, database, cache, or infrastructure component, and each edge represents a dependency with a measured latency and error rate. When an incident occurs, this graph becomes the map that the AI traverses to find the origin of the problem. The second layer is change correlation. Every deployment, every configuration change, every infrastructure modification is indexed as a change event with a precise timestamp. When an anomaly is detected, the system automatically asks the question, what changed in the 30 minutes or the 2 hours or the 24 hours before this anomaly began? Change to incident correlation is one of the most powerful signals in automated RCA because the vast majority of production incidents are caused by change. The third layer is historical pattern matching. If your system has experienced a similar symptom pattern before, the AI retrieves the previous incident record, identifies what was confirmed as the root cause, and what remediation was applied. This is essentially institutional memory that never forgets and is available to every engineer on your team at 3 a.m., including the engineer who joined last month. The fourth layer is natural language generation. Platforms like Dynatrace, Grafana, and emerging tools built on top of large language models are now generating plain language incident summaries, not a wall of metrics. An actual paragraph that tells you something like, a memory leak in the payment service introduced in the deployment at 1432 UTC is causing pod restarts every 18 minutes, which is increasing P99 latency on the checkout endpoint and affecting approximately 2,300 transactions per minute. The recommended action is rollback to the previous image version. That is not magic. That is structured telemetry plus causal graph traversal plus change correlation plus a language model handling the output formatting. But the result is an on-call engineer who gets to the right answer in 2 minutes instead of 2 hours. Now here is the critical caveat every performance engineer needs to understand. Automated RCA is only as good as your observability coverage. If a service is not instrumented, it is invisible to the causal graph. If your deployments are not tagged consistently, change correlation breaks down. If your SLOs are not defined, the system does not know what normal looks like. The AI is not smarter than your data. It is faster at processing the data you already have. That is the distinction. That is what drives everything. Quick pause here. If you are finding this valuable, the single best thing you can do right now is hit the subscribe button and turn on notifications. We cover real-world performance engineering on this channel, not textbook theory. And in the next section, we are getting into something that directly affects your day-to-day work as a performance engineer. AI-augmented load testing. This one is going to change how you think about your entire test strategy, so do not go anywhere. Section 4, AI-augmented load testing. Load testing in 2026 looks fundamentally different from load testing in 2022. And I want to be specific here because this is an area where a lot of teams are still operating the old way without realizing what they are leaving on the table. Traditional load testing workflow. A performance engineer analyzes production logs, identifies representative user journeys, writes test scripts manually in JMeter or K6 or Gatling, defines ramp-up profiles based on intuition or past data, runs the test, analyzes results manually, and writes recommendations. That entire process can take a full week for a complex system. And the moment your application changes significantly, those scripts become outdated and need to be rewritten. AI-augmented load testing changes 3 specific parts of that workflow. The first is automatic test generation. Modern platforms can analyze your OpenAPI specifications, your production traffic logs, and your distributed traces to automatically generate realistic load test scenarios. Tools like K6 integrated with Grafana Cloud AI features and platforms like Gatling Enterprise are moving directly in this direction. Instead of manually writing test scripts, you describe the behavior you want to validate, and the system generates the script. For teams running continuous testing as part of a CI/CD pipeline, this means every deployment can be automatically tested against a scenario that reflects current application behavior, not a scenario that was written 3 months ago when the API looked different. The second change is intelligent scenario modeling. Traditional load tests use predetermined traffic shapes. Ramp up to 1,000 virtual users, hold for 10 minutes, ramp down. That is fine for regression testing, but it does not reflect how real users actually behave in production. AI-augmented platforms can generate adversarial traffic patterns, meaning traffic specifically designed to find the edge cases your system struggles with, based on historical failure data. They can model correlated user behavior, where a spike in search traffic predictably triggers a spike in recommendation service load 30 seconds later. They can simulate geographic distribution effects, time-of-day behavioral shifts, and API interaction chains that no human test engineer would think to write manually. The third change, and this is the one with the biggest operational impact, is continuous performance validation. The old model was run a load test before a major release, usually the night before go live. The new model is run automated performance validation on every pull request, with AI-generated scenarios that adapt to the code changes in that specific PR. If your PR modifies the checkout service, the AI generates a test focused on checkout flows. If you change the database schema, it generates a test focused on query-heavy workflows. This is performance testing as a first-class citizen of your development process, not an afterthought before go live. For teams using JMeter today, the path to AI augmentation typically runs through integration with AI-powered test data generation tools and result analysis platforms that can automatically identify performance regressions across test runs. Prioritize which regressions require human investigation. The script writing stays in JMeter. The intelligence lives in the surrounding toolchain, and the combination is far more powerful than either one alone. Section 5. Adaptive alerting and AI noise reduction. I want to spend real time on this section because alert fatigue is, in my opinion, the most underrated and most damaging problem in the performance engineering space right now. Here's a number that should make you uncomfortable. According to research by Gartner, the average NOC, or SRE team, receives somewhere between 1 million and 10 million alerts per month. Of those alerts, studies consistently show that between 70 and 99% are either false positives or duplicate signals representing the same underlying issue, generating noise across multiple monitoring tools simultaneously. Let that actually sink in. Your engineers are spending the majority of their alerting response time on alerts that do not represent real problems. And the real critical problems are getting buried in that noise. This is not a monitoring configuration problem. This is a systems architecture problem. Adaptive alerting in 2026 uses AI to solve this at 3 levels. The first level is dynamic threshold management. Baselines are learned from system behavior, not hard-coded by an engineer who guessed. But adaptive alerting goes further than just learning baselines. It also adjusts alert sensitivity based on business context. During a major product launch or a marketing campaign that the system knows about through calendar integration, alert thresholds and priorities automatically adjust. The system knows this is an unusual but expected traffic period. It does not page your team about a 40% traffic increase that the marketing team announced 2 weeks ago. The second level is alert correlation and deduplication. When a database instance goes down, it does not generate one alert. It generates alerts from the database monitoring tool, from every service that depends on that database, from the load balancer that starts seeing errors, from the synthetic monitoring platform that detects endpoint failures, and from the business metrics dashboard showing a drop in successful transactions. That is potentially 50 to 100 individual alerts for one root cause. AI alert correlation identifies that all of those signals point to the same underlying event and collapses them into a single incident record with a confidence-ranked list of potential causes. Your on-call engineer gets 1 notification instead of 100. The third level is alert routing intelligence. Not every alert needs to go to every engineer. AI-powered alerting platforms learn which engineers have the context to address which types of incidents. what the right escalation path is for different severity levels, and what time of day factors should influence how an alert is delivered. The result is that the right person gets the right information in the right format at the right time. The most important architectural decision you make when implementing adaptive alerting is defining your signal hierarchy. Not all telemetry is equally valuable for alerting. User-facing SLO breaches are always top priority. Internal service SLIs are secondary. Infrastructure metrics are tertiary, because infrastructure problems that actually matter will always surface as user-facing impact first. Build your alert hierarchy around SLOs rather than infrastructure metrics. That single architectural decision is what makes everything else work. Section 6, the new performance engineer in 2026. Everything I have covered in this video points to a fundamental shift in what the performance engineering role actually means in 2026. And I want to be direct with you about this, because I think there is a lot of misplaced anxiety in the industry right now. AI is not replacing performance engineers. AI is making performance engineering harder for anyone who is not willing to grow. Let me explain what I mean by that. The old performance engineer skill set was this: know your load testing tool, know how to read a metrics dashboard, know how to analyze a JVM heap dump, know how to tune a slow database query. Those are still relevant skills, but in 2026, they are table stakes. They are the floor of the profession, not the ceiling. The new performance engineer operates at a different abstraction layer. You are not just running tests anymore. You are architecting the entire performance validation system. You are defining SLOs that have real business meaning and are tied to real revenue impact. You are designing the observability instrumentation strategy so that AI systems have the data quality they need to function effectively. You are building closed-loop remediation architectures. You are the person who evaluates which AI performance claims from vendors are real and which are marketing noise. You are the person who decides what the AI should be trusted to do automatically, and where human judgment is non-negotiable. The skills that matter most in 2026 are these: observability architecture, understanding OpenTelemetry deeply, understanding distributed tracing, knowing how to design instrumentation that produces high-quality telemetry at scale, SLO engineering, knowing how to define meaningful service level objectives, calculate error budgets, and use those error budgets to drive engineering prioritization, AI tooling literacy, understanding what these AI systems are actually doing under the hood well enough to evaluate their outputs critically and configure them intelligently rather than blindly trusting vendor dashboards, and systems thinking at scale, the ability to reason about complex distributed systems as integrated wholes, not just as collections of individual services. The performance engineers who are thriving in 2026 are the ones who invested in these higher order skills over the past 2 years, not the ones who optimize their manual test scripts. That is the honest picture. And one more opportunity I want to flag before we close this out. The rise of AI in performance engineering is creating an entirely new specialization that very few people are qualified for yet: AI performance testing. Specifically testing the performance of AI and machine learning systems themselves. This is a discipline with unique challenges around model inference latency, GPU utilization, embedding retrieval performance, and large language model token throughput. If you want to be ahead of the curve in 2026, this is the space worth investing serious time in. The demand is there. The qualified engineers are not. Let me bring all of this together. In 2026, AI is transforming performance engineering across 5 major dimensions. AI-driven observability is replacing static thresholds with dynamic learned baselines that catch problems before they become incidents. Self-healing Kubernetes systems are closing the loop between detection and remediation, handling known failure modes automatically with confidence-gated actions. Automated root cause analysis is encoding expert reasoning into systems that identify the cause of an incident in minutes instead of hours. AI-augmented load testing is making continuous performance validation practical at the pace of modern development. And adaptive alerting is finally solving the alert fatigue problem that has been undermining engineering effectiveness for years. But the thread running through all of this is the same: the performance engineer's job is not disappearing. It is evolving into something more strategic, more architectural, and more impactful than it has ever been. And the engineers who understand what these AI systems need, high-quality telemetry, well-defined SLOs, intelligent instrumentation, and sound architectural principles, are the engineers who will be most valuable in this new world. If this video gave you a clearer picture of where performance engineering is heading, I have two asks for you. First, subscribe to this channel. We go deep on exactly this kind of real-world, practical engineering content every single week. And second, drop a comment below and tell me which of these 5 areas you want to go deeper on in a future video. Self-healing Kubernetes, automated RCA, AI augmented load testing, adaptive alerting. Tell me what matters most to your work right now, and that is exactly what we will build next. Thanks for watching. Let us build reliable systems.